Okay, so let's come back to the pipeline again. So, okay, so if you look at the pipeline, there are so many different stages, right? So, modeling transformation, we've already talked about in the past lecture. And basically we talk about the ordering, right? This is a stack format, the ordering of transformation, which ones apply first, which ones apply next, How do you play with tricks? If I want to change the order on the fly, how do I do that? I get the model view matrix out to do the modification, all these kind of things, right? So this model view transformation is done. Rasterization, once again, was partially done by Rasmussen, right? Display is done. Projection is done. And now we're left with, this is left for the second part of the semester, right? Illumination, okay? So trivial rejection and clipping will be covered next lecture. So the only stage left is viewing transformation, okay? All right. So what is viewing transformation? So it seems that I have already covered that the projection from a 3D point to a pixel, right? That's what we talked about just now, right? If a 3D point X, Y, Z, how do you project it onto your screen so that it gets a pixel code, right? So that's sort of this very fancy matrix format, right? What we talk about. So seems we're done, right? Because we have the 3D points and you have the camera, then you seem to have done everything. But we're not. Because the projection, remember, the two models, the two versions I've shown you, right, corresponds to that either the camera lies at the origin, right? The camera lies at the origin. The image plane lies at the z equal to d, right? Or the image plane lies at the z equal to d, z equal to 0, and the center projection lies at the z equal to minus d. Right? Only two situations, right? These are two special situations, right? In reality, your camera can be arbitrary in 3D space, right? So that needs to apply another transformation so that I will align everything with respect to my camera. In other words, my camera's point of view after this transformation will lie at z equal to 0. Does that make sense? So because this projection is a special case, right? The projection says my camera has to lie at the origin, right? The center projection has to lie at the origin, right? The image plane has to lie at z equal to 1, right? But in reality, you can specify your camera on the fly, right? Makes sense, right? So you want one more transformation so that I can transform the world. That's the 3D geometry, where 3D geometry is defined. You can transform the world so that the camera by the end of the day will lie at the z equal to 0, right, at the origin. Does that make sense? Okay, so this is the second part of the lecture. We're going to talk about this viewing transformation. Okay, is it good? All right, so I'm going to do the, I'm not, you want to orient it towards me. Okay, all right, so yeah, I'm going to do the math again, okay? So now that the camera can be free will, okay, can be at any place. Before the projection, we said the camera has to lie at the origin with image plane to be z equal to d. That's what we said. Now that the camera can be anywhere in the 3D space, the camera can be anywhere at, I define some coordinate system. I call it I, X, I, Y, I, Z. So the camera can be anywhere in 3D space, okay? This is the position of the camera. Does that make sense? Okay? And it's looking at a point. Okay? All right? It's called a look at X, look at Y, and look at Z. It's looking at a 3D point. My eye is at a 3D point, and it's looking at a 3D point. Is it clear? Good. And my goal is to find a transformation T to the eye coordinate system, right? I want to transform the eye so that the eye will lie at the origin, right? Make sense, right? And the viewing direction will align with Z, right? Will align with Z. Is it clear? Okay, all right, so how do I do that? Well, first of all, I will need to know which direction I'm looking at, right? This is like which location I'm looking at. Does that make sense, right? So first I need to know which direction I'm looking at, right? And that should be pretty easy to do, right? How do I know which direction I'm looking at? Well, you have the origin, right? You have another point, right? So the difference between 2 points, right, will give you the direction. Does that make sense? Okay? So the first is the direction, right? The direction L. I think I should turn the light maybe so that it's captured easier. Okay? All right. So the direction L is corresponds to the difference between where I'm looking at and where I am, right? So the direction is simply look at minus I, right? So I just denote it as vectors, right? So it's easier for me. I'm not going to write x, y, z, but it's just 2 vector difference. Make sense? Is it good? Okay? And I want to normalize it. I'm going to normalize this vector, right? Okay? Is this clear? I have my I position, I, x, I, y, z. I'm looking at you. Here you are at the look at x, look at y, look at z, right? My first question is which direction I'm looking at, right? So by doing the subtraction, right, I will tell you which direction I'm looking at, right? And I'm going to normalize it to have a normalized. So I use hat to represent a normalized direction. Is it good? Okay. All right. So if I am looking at this location, okay, if I'm looking at this location, where do you think is my image plane? Well, my image plane must be perpendicular to this look at direction, right? Has to be perpendicular, right? So my image plane will look like something like this, right? That's clear enough, right? Makes sense, right? My image plane has to be perpendicular to my look at direction, right? Okay? And it has to form, this is my right, right? This is my right, right? And this is my up, right? U, right? Right? In your eye, on your retina, right? Your retina is perpendicular to your viewing direction, right? Your retina has a right, your retina has an up, right? Which is the 2 coordinates, right? Does that make sense? Good. All right. Okay. So the question is, how do I get my right and how do I get my up? Makes sense, right? That's totally a legitimate question, right? If I'm looking at this way, can you tell me where is my right and can you tell me where is my up with respect to my retina, right? Okay. How do I do that? In order to do that, I need an auxiliary direction, which is called the sky. I need to know where the sky is. Without knowing where the sky is, actually you can imagine I can rotate my image plane at will. Your retina can rotate at will, right? You have to know where the sky is to have a unique definition of what is right and what is up. Okay? All right, is it clear? Okay, so given that sky and L, how can you get either right or up? Look at this figure, right? If I know the sky and if I know the L is here, right? This is my L, right? Very good. Cross product to get what? Yeah, to get, I have 2 questions, right? I want to get R, right? I also want to get up, right? So when you say cross product, it's a correct answer, but it's so generic. First is what cross with what? Second is what do I get, right? So let's answer the easy question. What do I get? Right. Okay. What cross with what will give me right?
Sky cross with L.
That's another good question, another good guess. And remember, we have to follow my right-hand rule, right? Okay? Remember, I have to follow my right-hand rule. So sky is here. You can imagine, sky is here. I'm looking in this direction. They're not perpendicular, okay, first of all, right? Sky and my look at it does not guarantee to be perpendicular. Most likely, they're not perpendicular, right? Makes sense, right? So if follow you, sky dot cross with right, cross with look, right? L, sky cross with L, right hand rule, right? It will give me my left, right? So if I want to get it right, I will do L cross with my sky. You can do it yourself, right? I'm looking at this way. Sky is here. I want to know where's my right, right? Sky is here. I'm looking at this way. Look cross with sky equal to my right. Right hand rule. Does that make sense? Okay. So the right is equal to. Remember, sky is also normalized. Okay. I assume it's normalized. It's essentially sky cross with L. Does that make sense? Good? Okay? Alright, so this is how I get right. You can think about it when you look at it this way. You want to know this direction, you're looking at this direction. You have the sky, so of course it's this cross with this, which will be the right. Okay? Just imagine, then you will get to know the right. Okay? Alright, how do I get up? Now I have the look, I have my right? How do I get my up? Another cross product, right? Simply another cross product. Because I know my right and I know where I look, right? My up should be perpendicular to both, right? It's a 3 perpendicular axis, right? Okay? So in this case, is what cross with what?
Look to the right.
Hey, which one goes first, right? They're different, right? Again, my right hand rule, you should think about it, right? So my right is here, my look is here, right? My up is here, right? So it should be right cross with look. Right cross with look, give me up. Look cross with right will give me down, okay? Alright? Right cross with look, give me my up. So my up is equal to right cross with look. Is it good? Fair enough, right? Are we good? Okay, so step number 1, I know where my eye is, and I know where am I looking at. I will get my look at direction out. Okay, this is the first step. Get my look at direction out. All right, is it good? Okay. Then, if I know where the sky is, generally you assume you know the sky. Sky is 0, 0, 1. It's pointing up to the z-axis. Okay, you assume. Okay. Then, in this case, then I have the right is equal to, because I know where the sky is when I where I look at, it's the look cross with sky, which will give me right. And then finally, I know the right, I know where I look at, I know right cross with look, which will give me up. So cross product, which will give me 3 vectors. Are we good? Okay? Yeah.
So right is look cross with sky.
Right is sky cross with look, right?
So then sky cross with
Oh, you're right. I messed it up. Yes, you're right. So right should be look with the look cross with sky. Yes. All right. Okay. Is it good? Okay. Now that I know 3 vectors, right? I know look, I know right, I know up, right? So I have 3 vectors now. That's good. At least I know 3 vectors, right? And my next goal is to find a transformation T. When this transformation is applied to my camera, right? My camera's origin, my camera's center projection, right? Will go to the origin of the coordinate system. My camera's look direction will align with the z-axis, right? So that will allow me to use my projection equation I just derived just now. Because my projection has a very strong assumption. It says the center projection has to lie at the origin, and the viewing direction has to align with the z equal to with the z-axis, right? That's what we derived. We did not derive an arbitrary fix. This is impossible to derive more precisely, right? It's very complex, when you do projection. So we simplify that. We said, okay, we derive a special projection model. Basically, the special projection model, the center projection lies at the origin. The viewing direction aligns with the z-axis. Okay, that's what we derived. So now I give you arbitrary camera location. Okay, now I first apply transformation so that after this transformation, the eye will align with the origin, and the viewing direction will align with the z-axis. Is it good? Okay, so, all right, so this is right, this is up, this is my lookout direction. And you instantly find that does it make sense, or is this consistent with my x, y, z axis? Conceptually, you want the right to be my x, right? X-axis, right? You want my u to be my y-axis, right? Because it's your image plane, right? So it's a retina, right? It's your image plane. So conceptually, you want your right to be your x-axis, x-axis, right? And u to be the y-axis, right? And you conceptually want the L to be the z-axis, right? But if you think about it instantly, it doesn't make sense now. Because our coordinate system, once again, is the right-hand rule. If R is the x-axis, U is the y-axis, then according to the right-hand rule, my look must be the negative z-axis. Is it clear? Okay, that's a tricky part. So you compute the L, compute R, compute the T, compute the U. Your goal is, now that I assume these are all computed, now that I have three vectors, which is L, where I look at up my right, my up location on my retina, and my right on my retina on my image plane. And your goal is to find the transformation T, so that when this transformation T is applied to this, the location of the eye, will align with the origin, and the direction of viewing will align with not a z, but a minus z direction, because I have to follow the right-hand rule. If this is my x-axis, this is my y-axis, this has to be the negative z-axis. Does that make sense? Otherwise, it does not follow the right-hand rule. So if I rotate my coordinate system, after I rotate my coordinate system, if this right aligns with the x-axis, this u aligns with the z-axis, or y-axis, then this L must align with the negative z-axis. It cannot align with the z-axis because it does not, the coordinate system itself does not align with the right-hand rule. Okay? Alright? So I want to find a transformation so that it satisfies two conditions. The eye aligns with the origin O, right? And the second, the R aligns with the x-axis. The U aligns with the y-axis. And the L aligns with the minus z-axis. This is my three conditions. I want to find a magic transformation Z, so that after I apply this Z, the I aligns with the origin, R aligns with the x-axis, U aligns with the y-axis, Z aligns with the L aligns with the minus z-axis. That's my goal. Okay, so obviously this can be done by some kind of magic rotation, right? I can rotate it, right? I can rotate my coordinates, and this can be done by some translation, right? That's easy, right? I can translate it. I can translate this point to the origin, right? So this can be done by the rotation, and this can be done by the translation. This can be done by the rotation. Is it good? Okay, so now that it's just a composition of rotation and translation, right? So for translation T, okay, so let's use the T star, which is the composed transformation. Okay, so for the translation T, how much translation should I do? That's easy. My original I location is at IE, IX, IY, IZ, right? After the translation, I want it to be at 0, 0, 0, right? Okay, right? So how much translation? Huh?
Minus the x.
Very easy. Minus EX, minus EY, minus EZ, right? I do the minus EX, minus EY, minus EZ. Then I will align it with the origin. That's easy, right? Does it make sense? Okay. So after I apply this T, right, which is, so the first step I do is T minus EX minus EY minus EZ. Right? After I apply this translation, remember in ordering, right? I want to translate the camera to the origin, right? Then I want to apply rotation here, right? I want to apply translation first, rotation next, right? Because I want to move it to the center, then I rotate, right? Okay? So after the rotation, I want to make sure the right aligns with the x-axis, U aligns with the y-axis, L aligns with the minus z-axis. Make sense? Okay. In other words, this magical transformation matrix R. This is my magical transformation R. Okay? When it applies to my three vectors, R, U, and L, R, U, and L, okay? Right? It should go to be my x-axis, right? Makes sense, right? My y-axis, right? And my minus z-axis, right? This is my goal, right? I want to find the rotation matrix R so that after applied to the R, to the U, and to the L, it aligns with the x-axis, y-axis, and the minus z-axis, right? So change it a little bit because there's a minus z, which is very annoying. So I'll move minus z to here. That's equivalent, right? Right? I cancel out this minus, I have a new minus there. Doesn't make sense, right? Is it good? Are we good? Okay, so what is this? X-axis, y-axis, z-axis. X-axis is 1, 0, 0, right? Y-axis is 0, 1, 0, right? Z-axis is 0, 0, 1, right? So this is what? Identity matrix. This is an identity matrix. Does that make sense? Are we good? Okay. So again, I want to find a rotation matrix R so that when it applied to the three vectors we generated just now, right? The three vectors we generate by doing the double cross product, right? By knowing the sky, by knowing where I look at, first cross product give me right, second cross product give me up, right? So I have the three vectors. How do I compute it? I've already done that, right? I know how to compute it, right? Okay. So the question next is how to find the rotation matrix so that after I rotate my coordinate system, it aligns with x-axis, y-axis, z-axis, which is equal to the identity matrix, right? Okay, so what is R? From a linear algebra perspective, what is R? This is a matrix, right? Because R is a 3 by 3 vector, right? Rx, Ry, Rz, Ux, Uy, Uz, Lx, Ly, Lz, right? This is a 3 by 3 matrix, right? So R is equal to this multiplied by this should get you identity matrix, right? So R must be the inverse of this matrix, right? Right? It's very simple linear algebra. Two matrices multiplied together to give you identity matrix, right? Okay. Therefore, the R matrix must be the inverse of this matrix. All right. Okay. So, but there is one more trick. What's special about this matrix? R is perpendicular to U, right? U is perpendicular to L. L is perpendicular to R. Correct? They must be perpendicular to each other, right? Because I do the cross product, right? So they're perpendicular to each other, right? Look like this, right? Okay? So this matrix, we call that orthonormal matrix, right? It's an orthonormal matrix. They are perpendicular to each other, right? Okay, so what's the inverse of a orthonormal matrix? Anyone? It turns out to be the transpose. If you have an orthonormal matrix, they are all orthogonal to each other, and each one is a unit vector. The inverse of an orthonormal matrix is the transpose of an orthonormal matrix. Okay? Therefore, the final rotation matrix, R, is looking like this. The R vector is transpose, because it's transpose, right? The U vector is transpose, and then the minus L vector is transpose. So originally it's a column, right? Column, right? 3 column vectors, right? Now I do the transpose, column becomes row, column becomes row, column becomes row. So this is the row vector, row vector, row vector. And this is the ultimate rotation matrix. Okay, so in the midterm, I will give you some kind of example. I will give you your eye's location, and I will give you, it's out of power. Okay, so I'll give you the eye's location, and I'll give you where it looks at, right? And I will ask you to give me what's the rotation matrix R, and then what's the translation matrix T. Okay, is it good? All right, so again, I'm not going to all these slides. You can go back and watch these slides yourself, So again, the steps are as follows. Step number 1, you get where you look at, okay? You know where you look at, and you normalize it. This is step number 1, okay? Step number 2, you know where the sky is, okay? You know where the sky is. So you do the first, this is called up in the slides, but it's very confusing because I have another up there, right? You up there, okay? So it's better to rename it the sky, okay? In fact, in many renderers, okay, it's called the sky vector, okay? So you know where the sky is, and you know where you look at. You do the first cross product to get the right. Then you do the second cross product to get up. Now you get 1, 2, 3 vectors, right? You can compute. From this 1, 2, 3 vectors, we do all these mathematics, to show that how you compose this rotation matrix. Okay, it's very easy. Once you have the 1, 2, 3 vectors, you change the column vector to be row vector. Originally it's column, column, column. Now you rotate it to be row, row, row. That will give you the rotation matrix. Is it clear? Okay. And the final result is the composition. All these is just like orthonormal to translation, And the final composition of the view transformation matrix is first move your camera to the origin. So it's minus I, minus I, minus I, right? Second, apply the matrix, right? Apply the rotation matrix. Rx, Ry, Rz. Originally vertical, now becomes horizontal, right? Horizontal R, horizontal U, horizontal minus L. 0, 0, 0, 1. This is rotation matrix. And this is OpenGL's viewing transformation. Now that I'm almost done. I'm almost done with the task that how I map every 3D point into my camera. Right? I have a camera, arbitrary position in 3D space, right? I first apply this viewing transformation, right? So that the eye goes to the origin and the viewing direction aligns with the minus Z direction. Is it good? Okay? Then, because what I derived in the past half of the lecture is that then you can do the projection. Now that the projection is easy, very simple matrix, right? So it's the final composition of the viewing transformation and the projection. Is it good? Okay, so you may ask me the question, and I may ask you the same question. Why don't I put these two stages together? Am I right? So I derived the projection matrix, right? It's a matrix, right? It's a linear operation, right? It's a matrix. I also derived the viewing transformation, which is also a matrix, right? It's a linear operation, right? I can, in theory, put these two stages together, right? I can call it viewing transformation and the projection, right? But in my pipeline, I didn't. I split them, right? Why is that? Why do I split the two stages? You see, I can combine the stages, right? There's nothing prohibiting me, because my ultimate goal is to project a 3D point onto my screen to be a pixel, right? That's my ultimate goal, right? So conceptually, I should combine them, right? By the end, it is combined, right? I do the viewing transformation, then I do the projection, right? It is combined in the end, right? But in my pipeline, I purposely split them into two separate stages. Why?
Just for speed?
For speed, very good. How?
Because then you can do that on one pixel while you're doing the projection on another pixel.
Not for that reason. Because you can still combine them together. That does not, you don't have to split every operation into a pipeline, right? That's not efficient, actually. So remember, the ultimate goal for graphics is to render as fast as possible, right? And I want to render as few triangles as possible, right? So my ultimate goal is trying to throw away as many triangles as possible, right? Is it clear, right? Mm-hmm. So in order to throw away triangles, right, I have to do the viewing transformation to know which ones lie outside of my field of view. That's clear, right? I will have to know that, right? Then I throw away all these unnecessary triangles, right? Which is the clipping stage, right? Remember, there's an intermediate stage in the middle, right? I first align, then I throw away. Once I finish throwing away, then I do the projection. Is this clear? Okay, so this is the first tricky question, right? So I will ask you again in the midterm, right? So why don't I combine them together? Second question. Is viewing transformation more expensive or is projection more expensive? And the why? Which process is more expensive? Both seem to just conduct linear operations, right? It's just a matrix times something, right? Which one is more expensive? What do you think? These are all tricky questions. You have to think very hard to answer them, right? Yeah?
Well, you've already thrown away some of the vertices, some of the less operations.
Oh, sure. But that's a separate question, right? My question is like, per vertex per se, right? Per point per se, right? Is it more expensive to transform according to the viewing transformation, or is it more expensive to do the projection? Right? You're saying that I throw away many triangles, but my question is per point per se, right? Is it more expensive to do viewing transformation, or is it more expensive to do projection? Right? Remember, what's unique about this projection? Projection has my x, y, z, w. And I will need to do something divided by w. So, which one is more expensive? Projection is more expensive. Why? Because projection needs to conduct a division. Projection needs to conduct division, which is most expensive. Division is very, very expensive, right? You all know, right? So all other operations, like viewing transformation, all these transformations, this is multiplication, right? These are essentially multiplications, right? Multiplication is cheap, right? Well, not that cheap, but compared with division, it's still much cheaper, right? So projection is more expensive. Because projection, you have x, y, z, w, and you have this, go back to that. You need to compute the x, y, z, w, and then finally you need to divide every component by the w component, right? In order to get the projection. I mean, it's easy to understand. You need to do x divided by z, right? Right? In the formulation, right? You need to do x divided by z. So if x is divided by z, then this division needs to divide by z. So that's very expensive. Okay? That's why projection is very expensive. And as a general rule in the pipeline, we want to push this more expensive stage to the later stages, right? Because now that if I can throw away as many triangles as possible, then that's a huge save, right? Because the expensive part has been thrown away, you know. Those who require expensive operations is limited to a small number, okay? That's why projection is almost at the last stage, okay? Okay, almost the last stage, right? The last stage is actually rasterization, right? Which is filling the holes, all these kind of things, right? And display, you know, this is the last stage. But it's almost at the last stage because projection is so damn expensive, right? Okay, is it good? Okay, so coming back to both, okay? So once we talk about the projection, we talk about viewing transformation. I have one more thing I need to talk about. That is, remember, the camera's field of view. I still have not specified the camera's field of view, right? So the camera's field of view basically is specified using two ways in OpenGL. The first way is directly called the GLU perspective. Okay, GLU means the GL utility. Utility means the camera utility. Okay, so GLU perspective, you can specify the camera in two ways. Either using this way, which is mostly commonly used, GLU perspective. You specify basically the this is a projection matrix. Okay, this is not the viewing. Okay, this is projection. So you specify the vertical field of view. You specify the horizontal vertical aspect ratio. You specify the near and the far. Remember, it's a it's a field of view, right? It's a fixed boundary, right? It's a fixed boundary. It's defined by left and the right, top and bottom, near and far, right? We give a fancy term. We call it a view frustum. Okay, view frustum is a fancy term. Okay, so within this view frustum, okay, you can define the camera in two ways. You can define it by the near and the far, and you can define by the vertical field of view and the horizontal field of view. Horizontal field of view is defined by the aspect ratio. Okay, is it clear? Okay, so this is the defined my field of view notation. Alternatively, you can define the view frustum in the other way. You can say the world is basically restricted as left or right, top, bottom, front, back. Okay, so you can directly define the GL frustum using left to right, bottom, top, near, far. Okay, you can define in two ways. Okay, so using this is not very straightforward, right? Generally, you won't specify a camera by saying the camera can only see this part of the world. It's very ridiculous, okay? You specify the camera this way. Most often you use a GLU perspective. You say, okay, my camera has a vertical field of view is how many degrees, and has an aspect ratio how many degrees, what's the aspect ratio, and you specify near and far, okay? So, by the way, the near and the far is what I'll talk about next week, okay? Is used for, once again, for throwing away as many triangles as possible. You basically confine your world within this sort of like prism shape, right? So everything lying outside of this world will be thrown away. So the question obviously is, how do you know which triangle lies inside and which triangle lies outside, right? In this view frustum, right? So this is a trick which we'll talk about next lecture. Okay? So this is called clipping, all right? So this is the projection. This is projection. This assumes the camera is already moved to the origin and the viewing direction is aligned with my minus z direction. Okay? All right? And to achieve this viewing transform, once again, everything I did, everything I have talked about is just one line of code in OpenGL. So, but I think it's essential to know what this OpenGL does, right? It's just one line. So the two functions, this projection and this viewing transform, two lines of code. The first line is GLU look at. That is my viewing transform. Where is my eye? My eye's location. Where am I look at? Center, center, center. Where is my sky? Sky up, sky X, Y, Z. So easy, right? Very easy, right? But I just like spent the whole hour explaining how it's done, right? So this is one line saying, where is my camera? Where am I looking at? Where is my sky? Okay, and then the second is, once I specify the viewing transform, I specify my camera parameter using GLU perspective. They always combine together. This says, what's my field of view? Okay, is it good? Okay, the two lines I just described basically, you know, it's the whole lecture, you know, on this projection and the viewing transform. All right, any questions? So you will talk repeat what I said today, I guess, on Wednesday. You know, also help them with the 3D transformation. All right, okay. All right, any questions regarding viewing transformation and the projection? No. Right. I think it's pretty straightforward, right? It's a lot of math, but at least you know what we're trying to do, right? Move the camera to the origin, align the viewing direction, right? Do the projection, right? That's what we try to do, right? Next lecture is about throwing away everything outside of my volume, right? How do I throw it away very efficiently, right? That's the trick. All right. Okay. Next thing is, how many of you have taken? I know you have taken my 320, right? How many of you have taken my 320? Okay, all right. So that's good. So let's talk about something. I think many of them, like who are not here, you know, have already looked at this. So that's very nice. We talk about, you know, viewing transformation. We talk about this projection. Now that you can project every 3D point onto my screen, so I'm happy, right? But there's one more catch. You project every 3D point on my screen now. Is you're not done yet. Because, for example, both of you are projected onto my screen, right? But you are lying in the front, you're lying in the back, right? You're sitting in the front, you're sitting in the back, right? So, as a matter of fact, I can only see you because you're not transparent, right? You're opaque, right? So, the different 3D points, right, can project to the same pixel, right? In other words. And I need to have a way to tell which one lies closer to me. and which one lies further away from. That's called visibility, right? I still need to, I resolve the viewing transform, I resolve the projection. I still need to resolve one more thing. That is, I need to resolve visibility. Because multiple entities can project to the same area onto my image plane, right? I need to resolve which one is further away, which one is closer. Does that make sense? Okay, so how do I do that? Well, the way you do that is something called the painter's algorithm. Okay? So the reason it's called the painter's algorithm is mainly because how oil painting is done. So remember, when people were doing oil painting, right? Oil is an opaque material, right? There's no transparency, right? So when people do oil painting, they always draw things furthest away. Does it make sense, right? They first draw one layer, that's the furthest away layer, right? Then apply oil to the second layer, right? So third layer, fourth layer, right? They always draw from furthest away to nearest. Does it make sense? Okay? So in other words, if I am able to draw every one of you in the right order, because my camera is fixed now, right? If I will know the relative position of every one of you, right? If I have a way to order you guys, right? Then I'm going to draw you correctly. Does that make sense? All right. But there are two major issues. First, it seems that in order to draw it correct, I will have to order you guys, right? But we're talking about ordering millions of triangles, right? Remember, like in 320, right? What's the complexity of ordering, of sorting, right? The best is, right, n log n, right? You can't do better than that, right? So n log n is the best, right? You're doing 1 million, and you will spend 1 million log 1 million to do the sorting. Cannot afford that. And you're doing it for every frame, remember? So you cannot afford that, right? So you cannot do the sorting prior to rendering, right? Cannot. You have to do it on the fly, right? Okay? Does that make sense? Okay, so the second way is basically I want to have a mechanism that I do this sort of ordering on the fly, right? Okay, I cannot do the pre-ordering because it's too expensive, you know. But I want to do it ordering on the fly. Okay, so there are two different approaches. Okay, all right. The first approach is called per pixel based visibility. Okay, all right. There are also two approaches in this category. Okay. The first approach in per pixel based visibility is why it's called per pixel based. Basically, you want to measure for every pixel which object is visible, which object is not visible. Okay, that's why it's called a per pixel based visibility. Okay, versus the other one is per triangle based, right? So it's the other opposite way. Okay, so for per pixel based visibility, any suggestions like how do I resolve the visibility from? Well, from every pixel, what can I do? What? Sure. So you say that for every pixel, I can sort of find the distance to what? But I don't know which object, right? Correct, right? I don't know which object, right? I don't know which object intersects me, right? So what I need to do is, the first algorithm in per pixel based, okay, is like you said, probably don't need that. I always think like showing sides is boring, so. So the first approach is, for every pixel, like you said, I want to decide which object is nearest to me, right? To do that, I'm going to do the following. For every pixel, I'm going to shoot out a ray. Because you know the camera, right? You know the center projection, right? You know where your camera is, right? And you know the location of your image plane, right? This is defined by viewing transform, blah, blah, blah. There's always a way, right? To determine, for every pixel, I can shoot out a ray, right? Correct, right? Then what? Then I'm going to intersect this ray, right? With everything in my scene, right? Does it make sense, right? Once I do that, then I will, like you said, I will determine the distance, right? Well, I will intersect every one of you, right? Okay, I may miss some of you, right? But for those intersect with my ray, I'm going to compute the distance, right? And then which one do I pick? The one with the smallest, right? The nearest, right? The nearest one, the smallest distance, right? Makes sense, right? And this is called the ray tracing or ray casting. Okay? Ray tracing or ray casting. For every pixel, I shoot out a ray. And I intersect the ray with every possible triangle in this world, right? Then I determine the nearest one. Is it good? Okay, so what's the complexity of this algorithm? Assume my image has a resolution of n pixels, okay? It's n by n, I assume, you know? N by n, okay? I just use n to account for all the number of pixels, right? And the world consists of m triangles. Okay? The world has m triangles, right? I have n pixels, m triangles, right? What's the complexity of my algorithm? For every pixel, I need to intersect all m triangles, right? And then pick the smallest one, right? Make sense, right? And then what's the complexity? It's very simple, n times m, right? For every pixel, I shoot out the ray, intersect all m ones, right? Pick the smallest one. You say, oh, pick smallest one seems complex. No, it's not. It's easy. You just keep a temporary variable, right? Which stores what's the latest, smallest one, right? Okay, so it's O1 operation, okay? Finding the smallest one is O1 operation. You can go through all of them. You're done, you know? All right, so it's n times n operations, right? This is for ray casting, right? Is it a good algorithm? It's a pretty bad algorithm. Because for every pixel, you need to compute m intersection, right? So generally, you're rendering image like 512 by 512, right? A quarter of 1 million pixels, right? So let's say it's about 1 million pixels, right? So it's a 1K by 1K image, is 1 million pixels. You have 1 million pixels, right? And you're seeing, let's say, a very simple thing contains 1K triangles, right? 1,000 triangles is nothing, right? Very simple. Right? Correct? For everyone, you need to do 1G operations, right? You have 1 million pixels. You have 1K triangles. You need to do that many operations for a single frame. That's a lot of computation, right? That's a lot of computation. Do you agree? Okay. So this is called the ray tracing. This is called the ray tracing. Doesn't work very well for resolving visibility. So what's the better one? So the first idea is the idea, we're just doing brainstorming, right? The first idea is for every pixel, shoot out the ray, intersect the ray with all possible triangles, right? Okay? What's the opposite of that?
Use the triangles and
Back project, right? Very, very good. So the second option is for every triangle, right? I map it onto my screen, right? Is it good, right? But how do I guarantee visibility in that case? Remember, my goal is to solve visibility, right? So what about the green triangle comes first, right? And the blue triangle comes later. So how do I resolve which one is visible, which one is not visible? Right? You're right. You're on the complete right track. I want to do the back projection. I want to do rasterization. Okay, what's rasterization talk about, right? I have a triangle I want to rasterize onto my screen. I want to do rasterization. But how do I use rasterization to solve my visibility problem? So you map a triangle onto my screen. Now the second triangle comes in, right? Now I need to make a decision, right? Which one do I pick, right? Huh? Yeah, the near one. But how do I do that? Physically implement that. You're doing chicken egg, yeah.
you take the center point of the triangle and then you take the distance from the center point of that triangle to your camera.
Very good. Okay, very good in the sense that I'm going to say you're wrong. So, so very good in the sense that it sounds like a plausible idea. So the idea is that I take one triangle in, right? So which triangle do I pick, right? So I don't know. So first triangle comes in. So I measure the distance. Like you said, the reason is that I don't know if a triangle comes in, how do I measure the distance? So I have to have some hack, right? The hack you suggest is like, I pick the centroid, right? I pick the centroid of the triangle, right? Measure the distance of the centroid to my camera, right? So this is the distance. I call that the distance from the triangle to my camera. Okay? Now the second triangle comes in, I measure the same distance, right? Then I decide which one to pick, right? That's your suggestion, right? Okay? And I claim that won't work. Why? Or at least I claim that will not always work. It may work most of the time, but sometimes it can fail. Here's an example. Triangle red occludes triangle green, green occludes blue, blue occludes red. So according to you, whichever comes, right, there must exist one triangle that completely lies on the screen, right? It cannot be partial occlusion, right? But I don't know where do they overlap, right? I cannot even tell where they overlap, right? Okay. All right. But that's a very clever idea. We'll come back to this in a second, okay? That's a very clever idea, yeah.
Can you split the triangles into little tiny triangles?
Very good. So first of all, you look at this example, you realize my algorithm will not always work. Because if I measure the distance, according to the distance, at least one of them will be the nearest, right? Therefore, for the nearest one, I will just use its full color, right? But in reality, it's not the case. It's partial occlusion, right? One occludes the other. So no way this algorithm will work, right? Then you think about it. Okay, fine. Let me find a hack for that, right? The hack is I make the triangle smaller, right? Sure, that will partially work again, because you make the triangle smaller. How do you know it resolved my problem? Makes sense, right? But you can make it smaller. In this case, probably it will resolve the problem, right? But it does not always resolve the problem, right? The second downside is you're generally dealing with million level triangles, okay? Okay, sometimes trillion level triangles, okay? So million level triangles, you will soon find billion level triangles, you'll soon find if you divide them, you're just duplicating, you're generating a lot of overhead for memory, etc. Okay? So it's not a very feasible. Okay? All right. So this is one possibility. That is, you measure the distance of triangles, then sort of like resolve it, right? So coming back to your idea. Your idea was that I don't really need to deal with that. How about I know which one is overlapping which one, right? Let's deal with overlapping region, right? Does it make sense, right? Let's only deal with overlapping region. Okay? So, but how do I know? The question is, how do I know which part is overlapping, which part is not overlapping? Correct? That's a fair question, right? How do I know? You're doing the rendering. You don't know which one overlaps, which one does not overlap, right? How do I know which one overlaps, which one does not overlap? A very ugly hack, by the way. That is, you add a special hardware to that to tell you which one overlaps, which one does not overlap. But that overlap, that special hardware is called the Z buffer. It's called the depth buffer, Z buffer. Or depth buffer. So the idea is very simple. I want to apply your hack. But there's no way for me to apply this hack, right? My pipeline does not allow it, right? My pipeline does not support this operation. So what do? I add a buffer. I add a new buffer. Originally, I only have one single buffer, which is my frame buffer, right? Now that I add one buffer, which is called the depth buffer. Okay? So how it works? Each time you are rasterizing a triangle, you're mapping a triangle onto my screen, right? I'm going to compute for every pixel its depth. I'm going to store the depth at that depth buffer. This cannot be done in the previous pipeline, right? The previous pipeline does not support that. Does not allow you to store the depth value at every pixel, right? So what I do is I create a separate buffer. Each time a triangle comes in, during my rasterization, right? During my rasterization, when I map the color onto discrete pixels, I also store its Z value, its depth value. Does that make sense? Then a new triangle comes in, right? Then I will test for the pixels they cover, right? For the pixels they cover. Has its Z value had values already, right? If it does not have value, I will set its value, right? To be my current value. If the value has already been set, then I will do a test, right? Which value is closer to me? Does that make sense? Very straightforward, right? Along your line, basically I will have a separate buffer for measuring where are these occlusions, right? And then when these occlusions occur, how do I handle them? Does that make sense? Okay, so this is called the Z buffer. Okay, so the question for you. What's the complexity of Z buffer? Again, I have n pixels. I have n triangles, right? What's the complexity of the Z buffer? What's the worst case performance? Now we cannot talk about the performance, right? Very straightforward, right? So what's the worst case performance?
You should have a case where all of your triangles take up the whole space.
Exactly. So my worst case scenario is every single triangle covers every pixel, right? So it's again n times n, right? It doesn't help me much, right? All right. Does this happen? No way. In general, every triangle will occupy a tiny, 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 tiny portion of my screen, right? So it's in O n times n for sure, right? That's why when algorithm becomes nonsense, right? Because this O doesn't tell you any information, right? This big O is just that has a scalar there, right? In this specific case, it's most likely it's maybe 1 over 1,000 or 1 over 10,000 or 1 over 1 million. Really depends on, because you're looking at, a very high resolution image, right? So generally it's 1 over 1,000 to maybe 100,000. I don't know how many zeros that is. Great, right? So it times n times n. It is still in the order of n times n. But the scaling factor is critical. Because every triangle just covers a tiny little portion of your screen, right? Makes sense, right? Therefore, it's about this size pixels where I need to conduct M triangle, right? M triangle intersections, right? Okay, so this is much, much better than this. This is the depth buffer, Z buffer, is a much, much better algorithm for resolving visibility than raycasting. Okay? So now you ask me the question, so why didn't we do that in the first place, right? For multiple reasons. In ancient ages, right? In ancient ages of computers, okay? The most expensive part is what? It's not the CPU.
Memory?
It's memory. It's memory. In ancient ages, okay, the most expensive is memory. And the Z buffer is a very expensive memory. Why? Because it's not only a single byte per pixel. You're trying to resolve depths, right? The depth is in double of floating point, right? Okay? So a single byte per pixel is not enough, right? The depth buffer needs to be 32-bit, for example, right? Or 16-bit minimum, right? So it's a very expensive buffer. It's a very expensive buffer. So in ancient days, people cannot afford it. People have thought about it a long time ago, okay? It's no big news, okay? But they cannot implement it. It's too damn expensive, It's very expensive to implement Z buffer. Instead, people have to use some kind of like a ray tracing, okay? Some kind of ray tracing to resolve that. All right? Okay, so I have 4 minutes. I think we'll just stop here. And next time I will talk a little bit about, how do we accelerate this ray tracing algorithm. Before you're tracing about every ray for every pixel, right? So intersect with all M triangles. So we're going to play with some tricks to reduce this complexity, especially on M side. Conceptually, it's very straightforward. I do not need to intersect. For example, I'm looking at this direction, right? I'm tracing out the ray. I do not need to intersect my ray with every triangle on this side or every triangle on that side, right? I can restrict myself to a very small portion of triangles, right? Okay, so that requires building a fancy data structure, okay, which is called the binary space partition tree. Okay, it's a BSP tree. Okay, it's a very fancy algorithm trick. Okay, all right. Okay, that's all for today. I will see you next Thursday, right? Okay.